Hello everyone! The topic for today is how can we see atoms, ions or molecules. Before answering it, I am going to talk about the states of matter, the atomic structure and the electromagnetic spectrum. After that, I will describe some types of equipment. This will be used to give the answer to the following question. How can we see atoms, ions or molecules? In our world, it's easy to recognize three states of matter: solid, the gas inside the balloon, and liquid. However, there are two other states of matter. The fourth state of matter is plasma, when the gas is ionized at a pressure of 1017 atmosphere and a temperature of 108 Kelvin. Some examples of plasma are sun, stars, and electric arcs. The fifth state of matter is known as a Bose-Einstein condensation, when the elementary particles are cooled to a few billions of degrees above absolute zero. It undergoes a transition phase Bose-Einstein condensation and becomes a superfluid with zero viscosity. Here in the first picture, we can observe the distance among the particles is longer. In the second, the temperature is low and the particles become together. In the third, we can see a superfluid, that is, a liquid never stops fluid. We can watch a superfluid in this link. We know the periodic table of the elements. The elements are matter. They can be monoatomic and polyatomic. The noble gases are monoatomic. Helium is an example. Examples of polyatomic are sodium and oxygen. Here we can see two allotropes of oxygen, a triatomic molecule and diatomic molecule. Nowadays, the structure of the atom is described by quantum mechanics using observable properties. For example, it's possible to determine the electron density of atoms using X-ray titration experiments. The electronic density is the confined space that occupies one or more electrons. Therefore, from the experimental measures, it's possible to determine the electronic configuration of an atom. First, I want to say the atom is constituted by three kinds of particles: protons, neutrons, and electrons. These particles are matter. In this picture, I am showing a representation of the structure of an atom in the shell model. Here we can see the three fundamental particles. The protons and neutrons are in the nucleus, while electrons are moving around the nucleus, given different electronic density shells or levels. In green color is displayed the region where the electronic density seems to be zero. Here we can see that the level 1s is conformed by 1 to level S, the level 2 by 2 to level F and P, the level 3 by 3 to level S, P and D. Moreover, in the level 1 or sublevel 1 can be present until 2 electrons. In the level 2 can be present until 8 electrons. In the level 3 can be present until 18 electrons. That is, atoms are constituted in layers of electron density in a similar fashion than an onion. Therefore, from this representation, we can write the electronic configuration of atoms as to level 1s with 1 until 2 electrons, to level 2s with 1 until 2 electrons, to level 2p with 1 until 6 electrons, etc. In this case, electrons in 1s sublevel are the inner shell of the atom, and electrons in sublevel 2s and 2p are in the valence electrons. So, we can describe an atom with quantum mechanics. When the electron is moving around the nucleus, in this case, electron assumes a series of specific energetic states or eigenvalues. Each energetic state is described by 3 quantum numbers: the principal quantum number and the azimuthal or angular momentum quantum number L and the magnetic quantum number ML. Also, each state is named as orbital. Here we can observe that there is a direct relation between shells or levels with the principal quantum number. Level 1 with n equal 1, the second layer with n equal 2, the third layer with equal 3, etc. When an electron is moving around the nucleus, has an angular momentum described by the quantum number L or azimuthal. This azimuthal quantum number is directly related to the sublevels. Therefore, when the azimuthal number is 0, corresponds to the sublevel S. If the L equals 1, the sublevel P is present, and when L equals 2, the sublevel is named D. All charged particles in moving have a magnetic momentum. Thus, when an electron is moving around the nucleus, the possible magnetic momentum that the system can assume are determined by the quantum number ML. So, the different energetic states in an atom are determined by the combination of 3 quantum numbers N, L, and ML. These energetic states are denominated as orbitals. Therefore, we can say 1 is 1, the orbital or minimum energy that assumes 1 electron, where the quantum numbers are n equals 1, L equals 0, and ML equals 0. This is an example of isotopes. In the nature, there are 98.93% of 12 carbon and 1.07% of 13 carbon. If we see one atom of these isotopes, they have the same atomic same proton number in the nucleus, but the carbon 12 has 6 neutrons and 13 carbon has 7 neutrons. This information is important for some spectroscopy techniques. A photon could be studied as a wave, and therefore we can talk of the light. Light is a wave phenomenon, and therefore it could have different wavelengths. This is a table where you can see the different types of light according to their different wavelengths. The gamma ray waves are the highest energy. In contrast, the radio waves are the lowest energy. Now we can study the molecules, ions, or atoms using spectroscopy. In other words, the light falls on the molecules and they respond to that stimulus. Now, can we answer the principal question on how it is possible to see atoms, ions, or molecules? The answer is using spectroscopy. Here we can see some types of equipment: X-ray photoelectron spectroscopy, X-ray diffraction, nuclear magnetic resonance, infrared, Raman and infrared, and ultraviolet. This is a model for X-ray photoelectron spectroscopy. Two properties can be measured: the ionization energy and electron affinity. Here we can see other equipment with different functions. With this, we can perform X-ray photoelectron spectroscopy (XPS) or ultraviolet photoelectron spectroscopy (UPS), etc. The sample is put in this place after the light interacts with the sample at a specific wavelength with very high energy. For example, a wavelength of 23.7 nanometers, the valence electrons are removed. Picture, we can observe the experiment X-ray photoelectron spectroscopy. This methodology is used for ejecting of core electrons, whereas the ultraviolet photoelectron spectroscopy is employed for the elimination of valence electrons. Therefore, the ionization energy and electron affinity of the atom can be obtained. In the first case, is the energy required to remove an electron from a gas, atom, or ion. In the second case, is the energy required to remove an electron from gas, anion. The value of energy is positive. However, the electron affinity is also defined as the energy necessary to add an electron to a gas atom when the value of energy is negative. This is the spectrum of lithium obtained by photoelectron spectroscopy. We can see two signals of different intensity. The energy for removing a valence electron is less than the energy required to remove two electrons. In this other example, the electronic configuration of oxygen is 2 core electrons in the 1s orbital and 6 valence electrons in the 2s and 2p orbitals. Here we can observe that the 1s orbital has the highest energy with 52.6 megajoules per mole. In contrast, the 2p orbital has the lowest energy, 1.31 megajoules per mole. In this example, the ionization energy for gas carbon is 1086 kilojoules per mole. But we must be careful with the electron affinity, because when an electron is removed from the anion carbon, the value is plus 122 kilojoules per mole. In contrast, when an electron is added on the neutral carbon, the energy is minus 122 kilojoules per mole. The next piece of equipment is the X-ray diffractometer for a single crystal. A crystal is put on the goniometer and the energy depends on the wavelength of the X-ray tube source. If the lamp is of the copper, the wavelength is 0.15 nanometers. The X-ray is deflected when it crosses the crystal. After that, a diffraction pattern is obtained. The data are processed and the electron density map shows the molecular structure of the compound. The software can give the atomic model, for example. In the ribbons are represented the molecular structure of a protein. The X-ray technique, we can see the geometry of the atom in the molecule. For example, in the tetrachloroethene case, the geometry of zinc is tetrahedral. In the case of arsenic, is trigonal with pyramid. The carbon and nitrogen are trigonal only, or the oxygen are bent. Also, we can estimate the size of chemical bonds from the distance between atoms. So, in this molecule, the nitrogen copper chemical bonds are covalent. In contrast, the other nitrogen-copper interaction is coordination bond. Moreover, we can see the intermolecular interaction as the hydrogen bond between water and complex. Here we can see nuclear magnetic resonance equipment. This technique is very useful because the samples could be solid or liquid. Also, the compound must be dissolving in any deuterium solvent. The frequency to see the nuclei of 13 carbon isotope is 100 MHz and proton isotope is 100 MHz. This is a spectrum of 13 carbon NMR. Here, every signal represents the nuclei of carbon atoms. In this picture, we have 13 carbon and proton NMR spectra of this compound. In the 13 carbon spectrum, we find 4 signals for this compound. These signals are assigned to the carbon atoms 2, 2, 4, 4, 5, 5 and 6, 6. On the other hand, in the proton spectrum, the signals have a multiplicity due to the proton-proton interactions. Here we have infrared equipment. It's very useful because we can obtain a spectra of compounds in solid, liquid, and gas states. This is an equipment on which we can perform Raman or infrared spectra. The sample is put in this space for Raman or in this space for infrared, and therefore we can obtain Raman and infrared spectra. We can make different experiments of infrared. It's called near-infrared if the wavelength used to fall on the sample is between 800 and 2500 nanometers. In the medium infrared, the wavelengths are from 2500 to 50,000 nanometers. For the far infrared, the wavelengths are from 50,000 to 1 million nanometers. We know the infrared and Raman spectra show the different vibration modes of atoms. Therefore, we will recognize the functional groups of the molecules. This graph is a spectrum of glucose. These signals represent the vibrations of atoms that are contained in the functional group of molecules. For example, the signals for the hydroxyl group is BROAD. In this other example, we can observe the characteristic vibration signal of the carbonyl group, only for knowing a spectrum of Raman. Here we can observe the vibrations of copper, nitrogen, and copper chlorine. In the ultraviolet spectrum, we are promoting electronic transition from low to high levels in molecules. In this spectrometer, the sample is put in this place. This is the ultraviolet spectrum of glucose, sucrose, and xylox. In all cases, the signals are BROAD. In conclusion, we can see the atoms, ions, or molecules when the light interacts with the sample at different wavelengths using different types of equipment. To remove core electrons or valence electrons, we use the X-ray photoelectron spectroscopy. When we aim to see the electron density on molecules, the X-ray diffraction is used. To use the rotation behavior of nuclei isotopes, we use the nuclear magnetic resonance spectroscopy. But if we want to study the vibration modes of atoms in molecules, we use the infrared or Raman spectroscopy. Finally, the electronic transitions are studied using ultraviolet spectroscopy. You are young and you should be happy because you are studying and in the future. You are going to work in the laboratory and you will have results to present in the scientific meeting, and you are going to know other cultures and different foods. Also, I want to thank the English teachers Magdalena Marines, Marisol Jimenez, and Lisette Chavez. My colleagues Elena Otazo, Elizabeth Contreras, Karen Gonzalez, Elton Islas, and Rafael Tapia. I especially thank the students for the first semester of the major in food chemistry because they paid attention and They did some activities after the magistral lesson. Everyone gave me their comments to improve this work. Thank you for watching this video.